provide a comprehensive grounding system that effectively dissipates electrical current into the earth, ensuring safety and functionality of electrical equipment. The following components are used. Firstly, the main grounding electrode system. This includes two 3/4-inch by 10-foot copper-clad steel ground rods driven into the ground a minimum of 10 feet deep and spaced 6 feet apart. Two copper-clad steel ground rod clamps are used to connect the ground rods to the grounding conductors. A number 4 American wire gauge stranded copper wire connects the ground rods to the main bonding jumper. Secondly, equipment grounding. A number 4 American wire gauge stranded copper wire connects the main grounding electrode system to the main distribution panel, acting as the main bonding jumper. Equipment grounding conductors consist of number 6 American wire gauge stranded copper wire connecting all electrical equipment, including but not limited to a generator, transformer, uninterruptible power supply or UPS, power distribution unit or PDU, and generator paralleling switchgear. Thirdly, supplemental grounding electrodes, which are optional. If available and continuous, a metal water pipe may be used as a supplemental grounding electrode. Clamp number 4 American wire gauge stranded copper wire to the water pipe at the point of entry into the building. If available and continuous, underground gas piping may be used as a supplemental grounding electrode. Connect number 4 American wire gauge stranded copper wire to the gas piping at multiple points. Grounding resistance testing must be performed by a qualified electrician to ensure the effectiveness of the grounding system. Target grounding resistance is typically less than 10 ohms. All connections must be made with approved connectors and methods. The grounding system should be inspected and tested regularly to ensure proper functionality. Follow all applicable electrical codes and standards. The purpose of a grounding electrode system is to create a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers and fuses, thereby minimizing the risk of electrical shock and equipment damage. The main grounding electrode system typically involves driving ground rods into the earth. The depth and spacing of these rods are critical to achieve the desired grounding resistance. The National Electrical Code, or NEC, specifies minimum requirements for the size and type of grounding electrodes, as well as the methods for their installation. Ground rod clamps are essential for creating a secure and corrosion-resistant connection between the ground rods and the grounding conductors. These clamps must be listed for the specific purpose and compatible with the materials being joined to prevent galvanic corrosion. The grounding conductor, often made of copper, serves as the primary pathway for fault current to travel from the grounding electrodes to the main electrical panel. Its size is determined based on the size of the service entrance conductors, as specified in the NEC. The main bonding jumper is a crucial component that connects the grounded conductor, typically the neutral, to the equipment grounding system at the main service panel. This connection ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of voltage differences that could lead to electric shock. Equipment grounding conductors provide a low impedance path for fault current to return to the source from various pieces of electrical equipment. These conductors are typically run with the circuit conductors and connected to the equipment grounding terminals. The size of the equipment grounding conductors is determined based on the rating of the overcurrent protective device protecting the circuit. Supplemental grounding electrodes can enhance the effectiveness of the grounding system by providing additional paths for fault current to dissipate into the earth. Metal water pipes, if available and continuous, can serve as effective supplemental grounding electrodes. However, it is essential to ensure that the water pipe is electrically continuous and properly bonded to the grounding system. Underground gas piping can also be used as a supplemental grounding electrode, but it is crucial to avoid creating a direct connection that could introduce a potential ignition source. Grounding resistance testing is a critical step in verifying the effectiveness of the grounding system. This test measures the resistance between the grounding electrode system and the earth, providing an indication of how well the system will dissipate fault current. A target grounding resistance of less than 10 ohms is generally recommended to ensure adequate protection. When installing a grounding electrode system, it is crucial to use approved connectors and methods to ensure reliable and long-lasting connections. Connections should be made in accordance with the NEC and other applicable standards. Regular inspection and testing of the grounding system are essential to maintain its effectiveness. Grounding connections should be checked for corrosion and tightness, and grounding resistance should be tested periodically to ensure that it remains within acceptable limits. It is important to follow all applicable electrical codes and standards when designing, installing, and maintaining a grounding electrode system. The NEC provides detailed requirements for grounding and bonding, and compliance with these requirements is essential for ensuring electrical safety. The design of a grounding electrode system can vary depending on the specific characteristics of the site, including soil type, moisture content, and proximity to other underground utilities. A qualified electrical engineer or electrician should be consulted to ensure that the grounding system is properly designed and installed. In addition to the components mentioned, other elements can be incorporated into a grounding electrode system to enhance its performance. These may include ground enhancement materials, which are used to improve the conductivity of the soil surrounding the grounding electrodes. These materials can be particularly useful in areas with poor soil conditions or high resistivity. Another option is to use a ground ring, which consists of a bare copper conductor encircling the building and buried directly in the earth. A ground ring can provide a more extensive grounding path and improve the overall effectiveness of the grounding system. When working with electrical equipment and grounding systems, it is crucial to prioritize safety. Always to energize equipment before working on it and use appropriate personal protective equipment or PPE, such as gloves and safety glasses. Follow lockout-tagout procedures to prevent accidental energization of equipment during maintenance or repair. Regular training on electrical safety and grounding practices is essential for all personnel who work with electrical systems. This training should cover topics such as grounding principles, NEC requirements, and safe work practices. By following these guidelines, it is possible to create a comprehensive and effective grounding system that protects people and equipment from electrical hazards. Grounding electrode system for 400 amp service and equipment is a critical component for the safe operation of any electrical system. It provides a path for fault current to return to the source, allowing overcurrent protection devices to trip and energize the circuit. This helps to prevent electrical shock and equipment damage. The grounding electrode system consists of several components, including ground rods, grounding conductors, and bonding jumpers. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to provide a direct connection to ground. Grounding conductors are used to connect the ground rods to the electrical system. Bonding jumpers are used to connect different parts of the electrical system together to ensure that they are all at the same potential. The size and type of grounding electrode system required will depend on the size of the electrical service and the type of equipment being served. The National Electrical Code, or NEC, provides specific requirements for grounding electrode systems. It is important to consult the NEC to ensure that the grounding electrode system is properly designed and installed. In addition to the main grounding electrode system, supplemental grounding electrodes may be required for certain types of equipment. For example, generators and transformers often require supplemental grounding electrodes to ensure that they are properly grounded. Grounding resistance testing is an important part of maintaining a grounding electrode system. Grounding resistance testing should be performed on a regular basis to ensure that the grounding electrode system is still effective. If the grounding resistance is too high, the grounding electrode system may need to be repaired or replaced. A well-designed and maintained grounding electrode system is essential for electrical safety. By following the requirements of the NEC and performing regular grounding resistance testing, you can help to ensure that your electrical system is safe and reliable. The role of the concrete encased electrode, often referred to as a UVA ground, is to provide a highly effective grounding electrode by utilizing the concrete foundation of a building. This method involves encasing a bare copper conductor within the concrete foundation, creating a large surface area contact with the earth. This results in a low impedance path for fault currents enhancing the overall effectiveness of the grounding system. The NEC specifies requirements for concrete encased electrodes, including the size and type of conductor, as well as the minimum length of the conductor that must be encased in concrete. The advantages of using a concrete encased electrode include its stability, resistance to corrosion, and consistent performance over time. It is also less susceptible to changes in soil conditions compared to traditional ground rods. The connection of the grounding conductor to the concrete encased electrode must be made with approved connectors and methods to ensure a reliable and long-lasting connection. The location of the connection should be readily accessible for inspection and maintenance. When using a metal water pipe as a supplemental grounding electrode, it is crucial to ensure that the pipe is electrically continuous and properly bonded to the grounding system. This involves bonding around any insulated sections of the pipe, such as plastic fittings or couplings. The bonding jumper should be sized according to the NEC requirements and connected to the water pipe with approved clamps or connectors. It is also important to verify that the water pipe is in direct contact with the earth for at least 10 feet to ensure effective grounding. The use of underground gas piping as a grounding electrode is generally discouraged due to the potential for creating a hazardous condition. However, if it is used, it is essential to follow strict safety precautions and comply with all applicable codes and standards. The gas piping should be bonded to the grounding system at multiple points to minimize the risk of stray currents. It is also important to consult with the local gas utility company to ensure that the use of gas piping as a grounding electrode is permitted and to coordinate any necessary safety measures. The selection of the appropriate size and type of grounding conductor is critical for ensuring the effectiveness of the grounding system. The size of the grounding conductor is determined based on the size of the service entrance conductors, as specified in the NEC Table 250.66. The grounding conductor must be made of copper or other approved material and be protected from physical damage. The installation of the grounding conductor should follow the NEC requirements, including proper support and protection from corrosion. The grounding conductor should be run in a direct and unobstructed path to the grounding electrode system. The bonding of metallic equipment enclosures and other non-current carrying metal parts is essential for creating an equipotential plane and minimizing the risk of electric shock. This involves connecting all metallic parts to the equipment grounding conductor, ensuring that they are all at the same potential. The bonding jumper should be sized according to the NEC requirements and connected with approved connectors or methods. The bonding connection should be made in a way that minimizes impedance and provides a reliable path for fault current to return to the source. The maintenance of a grounding electrode system is crucial for ensuring its continued effectiveness. Regular inspections should be performed to check for corrosion, loose connections, and physical damage. Grounding resistance testing should be conducted periodically to verify that the grounding system is still within acceptable limits. Any deficiencies identified during inspections or testing should be promptly corrected to maintain the integrity of the grounding system. The documentation of the grounding electrode system is important for tracking its performance and facilitating maintenance. This documentation should include a schematic diagram of the grounding system, as well as records of inspections, testing, and repairs. The documentation should be kept in a safe and accessible location for future reference. The grounding electrode system is a critical component of electrical safety, and it is essential to ensure that it is properly designed, installed, and maintained. By following the requirements of the NEC and other applicable standards, it is possible to create a safe and reliable electrical system that protects people and equipment from electrical hazards. The grounding system, in essence, is an intentional connection from a circuit conductor or equipment to the earth. This connection establishes a 0-volt reference point and provides a safe path for fault current. Proper grounding and bonding are fundamental principles in electrical engineering to safeguard against electrical shock, minimize equipment damage, and prevent fire hazards. Grounding focuses on connecting the electrical system to the earth, while bonding involves connecting all metallic parts of the electrical system together to create a low impedance path for fault current. The NEC Article 250 provides comprehensive guidelines on grounding and bonding requirements for various electrical systems and equipment. Understanding the NEC requirements is essential for designing and installing safe and effective grounding systems. The grounding electrode system serves as the primary connection to the earth and typically consists of one or more grounding electrodes, such as ground rods, ground plates, or concrete-encased electrodes. The selection of the appropriate grounding electrode depends on soil conditions, local regulations, and the size of the electrical system. Grounding conductors connect the grounding electrode system to the electrical system and provide a path for fault current to flow back to the source. The size of the grounding conductor is determined based on the size of the service entrance conductors. Bonding jumpers connect different metallic parts of the electrical system together to ensure that they are all at the same potential. This minimizes the risk of electric shock if a fault occurs. Equipment grounding conductors provide a path for fault current to flow back to the source from electrical equipment. These conductors are typically run with the circuit conductors and connected to the equipment grounding terminals. Ground fault circuit interrupters, or GFCIs, are devices that detect ground faults and interrupt the circuit to prevent electric shock. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other transient events. SPD divert the surge current to ground, preventing damage to sensitive electronic components. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Grounding resistance testing measures the resistance between the grounding electrode system and the earth. This test provides an indication of how well the grounding system will dissipate fault current. Visual inspection should be performed to check for corrosion, loose connections, and physical damage. Any deficiencies identified during inspections or testing should be promptly corrected to maintain the integrity of the grounding system. Effective grounding and bonding are essential for electrical safety and should be a priority in all electrical installations. By following the NEC requirements and implementing proper grounding practices, it is possible to minimize the risk of electric shock, equipment damage, and fire hazards. Soil resistivity plays a crucial role in determining the effectiveness of a grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding, as it allows fault current to dissipate more easily into the earth. Soil resistivity varies depending on soil type, moisture content, and temperature. Sandy soils typically have high resistivity, while clay soils have low resistivity. Moisture content significantly affects soil resistivity, with higher moisture content resulting in lower resistivity. Soil resistivity also decreases with increasing temperature. Soil resistivity testing is performed to determine the soil resistivity at a specific location. This information is used to design the grounding system and select the appropriate grounding electrodes. Ground enhancement materials can be used to improve the conductivity of the soil surrounding the grounding electrodes. These materials typically consist of conductive minerals or chemicals that are added to the soil to reduce its resistivity. Proper selection and installation of ground enhancement materials can significantly improve the effectiveness of the grounding system. Understanding soil resistivity and implementing appropriate measures to reduce it are essential for designing effective grounding systems in various soil conditions. The application of equipotential bonding in swimming pools and spas is paramount to ensure electrical safety. Equipotential bonding involves connecting all metallic parts of the pool or spa structure, including the reinforcing steel, metal piping, and electrical equipment, to a common bonding grid. This creates an equipotential plane, minimizing the risk of voltage differences that could lead to electric shock. The NEC Article 680 provides specific requirements for equipotential bonding in swimming pools and spas. These requirements include the size and type of bonding conductors, as well as the methods for making the connections. Bonding conductors must be made of copper and be properly sized to carry the expected fault current. Connections must be made with approved connectors and methods to ensure a reliable and corrosion-resistant bond. Regular inspection and testing of the equipotential bonding system are essential to ensure that it is functioning properly. Bonding connections should be checked for corrosion and tightness, and the continuity of the bonding grid should be verified. Any deficiencies identified during inspections or testing should be promptly corrected to maintain the integrity of the equipotential bonding system. Equipotential bonding is a critical safety measure in swimming pools and spas, and it is essential to follow the NEC requirements and implement proper bonding practices to minimize the risk of electric shock. In healthcare facilities, the design and implementation of grounding and bonding systems are of utmost importance to ensure patient safety and prevent electrical hazards. Healthcare facilities contain sensitive medical equipment that can be susceptible to electrical interference and voltage fluctuations. Proper grounding and bonding minimize the risk of electrical shock to patients and staff, as well as protect sensitive equipment from damage. The NEC Article 517 provides specific requirements for grounding and bonding in healthcare facilities. These requirements include the use of isolated power systems in critical care areas, as well as stringent bonding requirements for all metallic parts of the electrical system. Isolated power systems prevent ground faults from interrupting power to critical equipment, while enhanced bonding minimizes the risk of voltage differences that could lead to electric shock. Regular testing and maintenance of the grounding and bonding systems are essential to ensure their continued effectiveness. Grounding resistance testing should be performed to verify that the grounding system is within acceptable limits. Visual inspection should be conducted to check for corrosion, loose connections, and physical damage. Healthcare facilities should have a comprehensive grounding and bonding management plan in place to ensure that the systems are properly maintained and that any deficiencies are promptly corrected. Proper grounding and bonding are essential for electrical safety in healthcare facilities, and it is crucial to follow the NEC requirements and implement best practices to protect patients and staff from electrical hazards. In industrial facilities, the grounding and bonding systems must be robust and reliable to withstand the harsh operating environment and protect equipment and personnel from electrical hazards. Industrial facilities often have large electrical loads and complex distribution systems, which can increase the risk of ground faults and electrical surges. Proper grounding and bonding are essential to minimize the risk of equipment damage, production downtime, and electrical shock. The NEC provides specific requirements for grounding and bonding in industrial facilities, including the use of dedicated equipment grounding conductors and the bonding of all metallic parts of the electrical system. Grounding conductors must be sized to carry the expected fault current, and bonding connections must be made with approved connectors and methods. Industrial facilities should conduct regular inspections and testing of the grounding and bonding systems to ensure their continued effectiveness. Grounding resistance testing should be performed to verify that the grounding system is within acceptable limits. Thermographic scanning can be used to detect hot spots in electrical connections, which can indicate loose or corroded connections. A comprehensive grounding and bonding maintenance program is essential to ensure that the systems are properly maintained and that any deficiencies are promptly corrected. Effective grounding and bonding are crucial for electrical safety in industrial facilities, and it is essential to follow the NEC requirements and implement best practices to protect equipment and personnel from electrical hazards.